So, having talked about the very, very big stuff in the universe, we're now going to move on to the very, very tiny stuff in the universe. And we're going to start with what is hopefully going to be a real quick recap about the structure of the atom and atomic models. So, hopefully you're all happy with the idea that that could be an atom. So we've got a positively charged nucleus where we find the protons and neutrons, which collectively we're going to call nucleons because they're things that are found in the nucleus. And the diameter of the nucleus is about 10 to the minus 15 meters, or 1 femtometer. You do need to know that number. We then should know that there are electrons that surround the nucleus that are orbiting it, and if we look at the atomic diameter, so the diameter of the entire atom, it's approximately 10 to the minus 10 meters. And again, that's a number that you're probably going to need to store away because it will be very useful. So it's about 100,000 times bigger than the diameter of the nucleus. Okay, so that should be old hat, except maybe we need to remember the numbers. The new thing I'm going to introduce today are atomic mass units, or AMU, or sometimes just U. They are a very useful unit. It's kind of like how we have for energy, we have joules, but sometimes we use electron volts if it's a very small amount of energy. Well, with mass we do the same. Kilograms are useful, but on the scale of an atom, not so much. So we tend to use these atomic mass units. One atomic mass unit is 1/12 the mass of a neutral carbon-12 atom. So that's approximately 1.66056 times 10 to the minus 27 kilograms, sorry. So what that means is that the mass of a proton is 1.0073 U, the mass of a neutron is 1.0087 U, the mass of an electron is 0.00055 U. So two things I just want to pull out here is that we can be very specific now when we're talking about these masses, and you can see that the mass of a proton and a neutron is different, and that is important. When we're just talking really generally and we're talking about subatomic particles, we tend to just talk about them being relative. So for the charge of a proton, for instance, we know it's 1.6 times 10 to the minus 19, neutron 0, and electron is minus 1.6. But you probably were used to talking about it as +1, 0, -1. For the most part, we're going to need to make sure we're being specific and doing it in coulombs, not this relative thing. So if we look at the mass of protons and neutrons, in kilograms on that scale, they're basically the same, and the electron is very, very tiny, which is why we used to say it was 1, 1, and pretty much negligible. But using this unified mass unit, we can come up with a much more accurate comparison between the masses of these various components. Okay, so a little bit of talk about the way that we write these down and the terminology that we use for them. So proton number of protons in an atom is often given the symbol Z. It's equal to the number of protons in the nucleus of an atom. It's also called the atomic number, and the atomic number is the same for all things that are the same element. It's the number of protons that decide what the element is. We've then got the nucleon number, which is often given the symbol A, and that's equal to the number of nucleons, so the protons plus neutrons in the nucleus of an atom, sometimes also called the mass number. Isotopes. Atoms have the same number of protons but different number of neutrons, and because they have the same proton number, they are the same element. Where we can write about isotopes, so that's one example, carbon-14, so I'm saying it's carbon, so it must have 6 protons, but it's got 14 nucleons. Another way I could write it would be to write it out like that, so use the symbol and the A and the Z number, or just use the symbol and then the 14. So in each of these I'm showing the nucleon number, because that's what makes it clear that it is an isotope, and I have the chemical symbol and or the proton or atomic number in there as well. Okay, so just a little bit on notation and definition of an isotope, which is something you need to know. Next thing I'm going to talk about is the strong nuclear force, which I briefly mentioned when we were talking about cosmology. And if you recall, I said that the strong nuclear force is what holds atoms together. Now, it is one of the 4 fundamental forces. So the 4 fundamental forces are the strong force, gravitational force, electromagnetic force, and the weak nuclear force. Weak nuclear force we'll talk about more later. Gravitational force you already know a lot about. Electromagnetic force you already know a lot about. So now let's learn a lot about the strong nuclear force. First of all, it is attractive between nucleons, so between neutrons and neutrons, neutrons and protons, and protons and protons. Its range is about 3 centimeters. It's very, very short ranged. And what it does is overcome the repulsion of the electrostatic force. Because I told you that we put all these protons together in the center of an atom, and it always amazes me that as students you never bat an eye at that we put all these positive things together, but you know that positive things repel each other. Well, the reason we can do it is because of this strong nuclear force. It's almost like Velcro that sticks the protons together, and at that short distance it's very, very strong, and it's so much stronger than the electrostatic force that it forces those protons to be close to each other. However, the strong nuclear force can also be repulsive. So if you have two nucleons that are getting too close together, so less than about half a femtometer, it becomes extremely repulsive. And that's a good thing, because it keeps the nucleons together inside the nucleus, but it also prevents them from being compressed together into a point, so it limits how much they can be squashed together. So you can't just basically squash something into nothingness, because the strong nuclear force prevents that from happening. So if we were to plot a graph of how it varies with distance, so here I've just got the size of the force and whether it is repulsive or attractive, and then I've got distances here. So this is about 1 femtometer and this is about 3 femtometers. So if we have a little look, the electrostatic force we already know about. Now the electrostatic force doesn't really act at less than this distance because that would be inside a nucleon, which the electrostatic force can't act. And all that happens with electrostatic force is that it decreases with distance and never really reaches zero, but just constantly decreases in this really positive, in this really simple way. Now because I'm inside the nucleus, the only things with electrostatic charge are going to be protons, so it's only going to be a repulsive force, which is why I've just got it on the repulsive side. If we now put the strong nuclear force on, it looks significantly different. So at this very short range distance, it's massively repulsive. The moment we cross over this 0.5, it gets very strongly attractive, and it peaks at about 1 femtometer, which is about the diameter of a very small nucleus. And it drops off to nothingness after about 3 femtometers. So it's distinctly different shape, which causes it to have distinctly different effects than the electrostatic force. Okay, so size of nuclei is something that we need to be able to calculate. And the radius of the nuclei is going to depend on the nucleon number. So more nucleons, bigger radius. If we look at fast-moving electrons, we can find that they have a wavelength that is about equal to the atomic diameter, which means that we can determine the radius of different isotopes. So by doing lots of electron diffraction, we've been able to measure the radius of atomic nuclei, and by doing that we've come up with this equation. So we've found that the radius of an atomic nuclei is equal to Rho times A, so the nucleon number to the power of 1 over 3, where Rho has an approximate value of 1.2 femtometers. So Rho is, if you imagine that we just had hydrogen, so 1 proton. So if I just had 1 to the power of a third, that would basically mean that the radius was equal to R0. And using this equation, we can calculate an approximation of the radius of a nuclei, assuming that we know the number of nucleons, which is going to be very, very useful. Okay, so that's as far as we're going to go with this bit today. Hopefully a bit of recap on stuff you already knew, then a little bit extra, what we're aiming for here. So remember, if you've got any questions, just make sure that you ask when you see me.